Now we'd like to explore how the intensity and the electric field, average electric field, drop off as you get far away from a source of light, a source of electromagnetic energy. Now, just as we saw in sound, as you get further away from the source, the area over which that energy is distributed gets bigger and bigger. Electric waves, electromagnetic waves from a point source, are expected to be spherical waves, just like we saw with sound. So the intensity is the power per unit area. Then we just put in the formula for area of a sphere, and the intensity will just be the total power divided by the area of a sphere, which is 4 pi r squared, the surface area. Notice the intensity falls off like the distance squared. Now, if we put that back into our equation that says the intensity is 1 over mu naught c times the RMS value of the electric field squared, then we can solve that for the RMS value of the electric field, and we find it's c times mu naught times the intensity, which is the power of the source, divided by 4 pi r squared. And then we take a square root to change it from being the RMS squared value to just the RMS value. The square root of 1 over r squared is just 1 over r. Notice that this implies that the electric field from radiation falls off much slower than the electric field from a static point charge. The electric field from a static point charge would itself fall off like 1 over r squared, whereas the radiation field falls off much more slowly, like 1 over r. This is one of the reasons why we can still see radiation fields from stars that are millions of light years away. But we would never be able to detect their electrostatic fields even if they had tremendously large charges, just because electrostatic fields fall off much more rapidly with distance.